I've got an interesting problem for you today. So let's say we're given the following function. I've called it f of x. It is e to the 2x times sine of 3x. And then our goal is to find the 30/30th derivative of f evaluated at 0. There's probably a bunch of ways to do this, but the way that we will do, we'll use techniques from linear algebra. And if you're interested in learning more things about linear algebra, you can check out my full course on my second course video channel, which is called Math Major. Link in the description. Okay, so let's get to it. So what we want to do is think about this e to the 2x sine 3x along with its companion, which is e to the 2x cosine 3x. And then we'll set v equal to the span of those two functions. What do I mean by the span of those two functions? I just mean all linear combinations of those two functions. So we'll talk about that a little bit. So this is e to the 2x sine 3x, and then e to the 2x cosine 3x. Great. And so let's notice that this is a two-dimensional vector space over the real numbers. And then what does an arbitrary vector inside of V look like? Well, notice V is a vector space made up of functions. So an arbitrary vector inside V is indeed a function. So any g of x inside V looks like, well, like I said, a linear combination of these two things. But to be a little bit more clear, it looks like a times e to the 2x sine 3x plus b times e to the 2x cos 3x, where a and b are real numbers. Great. So what that sets up is some sort of an equivalence between v and just the real plane. So let's put that here. So let's note that v is what we say in linear algebra, or maybe more particularly kind of in algebra as a whole, v is isomorphic to R2. And the isomorphism takes e to the 2x times sine 3x and matches it with the vector 1, 0. And it takes e to the 2x cos 3x and matches it with the vector 0, 1. Okay. So what's the point here? Well, we can think about the derivative action as being a linear transformation on the vector space V. And that sets up the following commutative diagram. So let's say we've got V going to V here. Here is our derivative. It's, well known that the derivative is a linear transformation on a space of maybe differentiable functions, which is exactly what we have here. And then down here, we have R2, and then we have this map right here, which matches e to the 2x sine 3x and e to the 2x cosine 3x with those two vectors. Maybe we could call that map T. So this goes here, and this goes here, like that. Then what we need to do is fill in the missing portion here. So we could fill in the missing portion here. Maybe we could call that capital D, where this capital D will make this diagram commute. And what I mean by saying this diagram commutes, it means that you can take any path from here to here and you'll get the same output. So if we map a function here from V to R2 and then use our D, it'll be the same thing as taking the derivative and then mapping it down. And I think we have just enough room over here to find out what this D is. And we can do it by taking the derivative of these two basis vectors for V. So let's notice that e to the 2x sine 3x prime, in other words, its derivative, well, that's something like 2e to the 2x sine 3x, and then plus 3e to the 2x cos 3x. Again, we just use the product rule there. Okay, but since this corresponds to the vector 1, 0, let's recall that, then that tells us that our map D should take 1, 0 to the vector 2, 3. So why is it the vector 2, 3? Because notice it's 2 times the function that corresponds to 1, 0 plus 3 times the function that corresponds to 0, 1. Okay. And then furthermore, we can see that e to the 2x times cos 3x prime, so its derivative, has a similar structure. So that's going to be equal to minus 3 e to the 2x sine 3x, and then plus 2 e to the 2x cos 3x. Okay. But again, using similar argument to this, we see that D must map the vector 0, 1 to, let's see, negative 3, 2. Like that. Again, because this guy right here corresponds to 0, 1, but then taking its derivative, this corresponds to negative 3 times 1, 0, and then 2 times 0, 1. Okay. But since D takes the basis vector 1, 0 to 2, 3 and the basis vector 0, 1 to negative 2, 3, we know that D has the following matrix form. We could write this down as 2, 3, and then minus 3, 2. So we've got something like that. Okay, so let's maybe summarize that stuff at the top, and then we'll move on to the next step. So far, we've seen that if we set v equal to the span of these two functions, then the derivative acting on a vector from v, in other words, a function, which is a linear combination of v, is equivalent to this matrix multiplying the corresponding vector in R2. Okay, so that's starting to look good. But now we want to push this diagram down one more step by diagonalizing this. And by diagonalizing it means that we can take an arbitrary large exponent of this matrix fairly easily. And that's in fact what we want to do. In fact, we want to find the 30/30th exponent of this matrix because we want to find the 30/30th derivative. So you could think of that as maybe just like putting all of these next to each other 3,030 times. Or maybe condensing it all down here with 30/30s for each, but we'll leave it like this for now. Okay, so like I said, we want to diagonalize this, but that means we need to find the eigenvectors and the eigenvalues. So let's start by finding the eigenvalues. And in order to find the eigenvalues, you always need the characteristic polynomial. So I think we called this thing D on the last board, so we need to find the characteristic polynomial of D. So that is P sub D of X, which is the determinant of, let's see, D times X, D minus the identity matrix times X. So let's notice that that will be the determinant of 2 minus X, and then here we have negative 3, 3, and then down here is also 2 minus X. So that determinant will be our characteristic polynomial. So let's see, that's going to give us P dx equals, so that'll be 2 minus x quantity squared, and then plus 9, just because of how the determinant works. Okay, so in order to find the eigenvalues, we need to set this equal to 0 and solve. So if we set this equal to 0, we'll see that we have x minus 2 quantity squared equals minus 9. You might say, well, we're about to take a square root and get complex numbers, but this was a real vector space. But we can expand it to a complex vector space just for the purpose of this diagonalization procedure. Okay, so that gives us something like x minus 2 equals plus minus 3 times I, which tells us that x equals 2 plus minus 3i. Okay, I think that's pretty interesting because the 2 goes with this exponent right here, and the 3 goes with this argument of cosine and sine. Okay, so now that we've got these eigenvalues, let's start to look for the eigenvectors. So let's maybe start with what I'll call lambda 1, which is 2 plus 3i. let's recall, in order to find the eigenvector, we need to look at the null space of this matrix D minus I times lambda 1. So let's write that down. We need the null space of D minus 2 plus 3i times the identity matrix. So it's something like that. Okay, but that's going to be equal to the null space of, so let's be careful here. We will have 2 minus 2, 2 minus 2, so that's 0 for the real part there. And then we'll be left with minus 3i on the diagonals, and then a minus 3 and a 3 on the off diagonal. Okay, but now row reducing does not change the null space, so we might as well start row reducing. Let's maybe do that by swapping the first 2 rows and then simultaneously dividing by 3. So that'll give us the null space of 1 minus I. Again, we swap that up and divide it by 3. And then we have minus I down here and a minus 1 down here. And then let's notice my second row is a multiple of my first row. If I multiply the first row by negative I, then you'll see that I achieved the second row. That means I can reduce the second row out of the situation. So I have my null space of 1 minus I and then 0, 0 right there. Okay, but now let's say that V, which is equal to our vector, maybe we'll call it AB, is in the null space of our matrix 1 minus I, 0, 0. So that means that our matrix 1 minus I, 0, 0 times our vector AB must be equal to the 0 vector. But that gives us an equation that relates A and B. That means that A minus I times B equals 0, which is the same thing as saying that A equals I times B. But that gives us a family of eigenvectors. But of course there's a family of eigenvectors, because if you have an eigenvector, then any multiple of that will be an eigenvector. So that means we've got some freedom. We might as well set B equal to 1, which tells us that A is equal to I. So that means that the eigenvector associated to this eigenvalue, I'll call that V1, is in fact equal to, let's see, I1, like that. Okay, good. And then you can find the other eigenvalue in vector pretty easily. So the other eigenvalue will clearly be equal to 2 minus 3i from that. And then if you've got a real matrix, which we do, the eigenvectors come in complex conjugate pairs. So that means the eigenvector associated to this eigenvalue will be minus I1. So that gives us a full eigenvector-eigenvalue system for our matrix D. Okay, so let's maybe summarize that up here, and then we'll keep going. Okay, so now we've got our eigensystem of D, which means we're ready to perform a diagonalization procedure. So let's set P equal to the matrix whose columns are the eigenvectors of D. So that'll be I1 and then minus I1. And then from a standard result from a linear algebra course, like the one I mentioned over there, we know that P inverse dP will be a diagonal matrix. And that diagonal matrix will have the associated eigenvalues on the diagonal. So here we have 2 plus 3i, 0, 0, and then 2 minus 3i. Okay, nice. So the way to put this in terms of this diagram is as follows. So if we map down here and down here to another copy of R2, maybe I'll say that this is R2 with a bar over it. Maybe that's not super standard notation, but that's like our R2 with a different basis. And then we can map across by this diagonalized matrix. So this is 2 plus 3i, 0, 0, 2 minus 3i. Okay, so what goes here and here will be represented by our path over here. And so notice to go from R2 back up to R, we need this to be P in this direction, which means in the way we've written it, it's P inverse. And then we'll go across by our matrix D. So that would be like going through here. And then down here will be another P inverse. Okay, so now we've got a good situation here. So we can maybe just say that's also a commutative diagram. Okay, and now we're essentially ready to do it. We maybe need to figure out P inverse though. So let's see, P inverse will be 1 over the determinant. So that's going to be I times 1 minus negative I times 1. So that'll give us 2I in the denominator. And then we swap the diagonals and negate the off diagonals. So that's the standard rule for the inverse of a 2 by 2 matrix. Then maybe we could write this instead of 1 over 2I as negative I over 2. That's sort of a standard way to do that. And then we can rewrite this as 1/2. And then let's see, we'll have a minus I here, a 1 here, an I down here, and another 1 right here. Okay, so that's our inverse of P matrix. And now we'll use the real power of this situation. And that power is the fact that this can be extended all the way down there 3,030 times, and then maybe contracted back to forget about all of the middle, so that we really have taking the derivative 3,030 times is the same thing as multiplying this matrix 3,030 times, which is the same thing as multiplying by this simpler matrix 3,030 times. Okay, so keeping that in mind, let's maybe get rid of this and then we'll finish it all off. So now we've got all of the parts in place and we're finally ready to finish it off. So here I've reminded ourselves that this map T takes the function e to the 2x sine 3x to the vector 1, 0, and then it does something similar to our other function. Then I've reminded ourselves what P and P inverse are, and just that this whole diagram is commutative. Okay, so now let's see. We want to take the, we want the 3,030th derivative of our function f. We'll plug in 0 at the end. Okay, well, let's notice that that's the same thing as the derivative operator being applied 3,030 times to our function f. Okay, but notice that going in this direction, so from here to here, is the same thing as going this big path underneath. So let's chart this big path underneath. Okay, so let's start with our function f of x. So I'm going to put it way over here to the right because we need quite a bit of room. And then mapping it down with t first, that'll be the first thing that we do. And then we'll map it with this P inverse matrix. So let's write that matrix. That's the matrix minus I by 2, 1/2, I over 2, 1/2. And then we'll map it across with this matrix. So let's see, that matrix is going to look something like this. We have 2 plus 3i all to the 30, 30. 0, 0, 2 minus 3i all to the 30, 30. That's because diagonal matrices have these nice forms. Okay, and then we're going to map up here by the inverse of P inverse, but the inverse of P inverse will just be P. So that's going to be I, negative I, 1, 1. And then finally, we're going to map back up here with what we're calling T inverse. That's because we need to go in the reverse direction. So let's see. That's what we need to end up calculating. Okay, so let's do it just from the right to the left a little bit at a time. So f of x is this e to the 2x sine 3x, and so that corresponds to 1, 0. So that means we can take this and just replace it with the matrix 1, 0. So that's actually pretty nice. Then from there, it's fairly simple to do this matrix multiplication. So let's see, if we do this matrix vector multiplication here, we'll get minus I by 2 and then I by 2. So something like that. And then bringing the rest down, so let's see, we'll need 2 plus 3i to the 30, 30, 0, 0, 2 minus 3i to the 30, 30. And then here we'll have our matrix I1, negative I1, and then here we'll have our T inverse. Good. So now the next thing to do is apply this matrix. So now the next thing to do is to do this multiplication right here. And so that's going to give us something like this. We'll have negative I over 2 times 2 plus 3i to the 30. That'll be in the first entry. And then in the second entry, we'll have I over 2, and then 2 minus 3i to the 30. Good. Okay, so that's starting to look good. Let's maybe bring that up and we'll finish it off. Okay, so this is where we left off in the last board. Now let's do this next matrix vector multiplication. So we still have a t inverse term, and then this will give us something like, let's see, I times negative I is 1, so we'll have 1/2 2 plus 3i to the 30, and then this will give us plus another half 2 minus 3i to the 30. So that's what we have in our first entry. And then our second entry will have essentially the same thing, but this multipliers will be negative I over 2 and I over 2. So minus I over 2, 2 plus 3i to the 30. And then plus, let's see, I over 2, 2 minus 3i to the 30. Great. And then just for the next step, let's introduce some notation. So let's say this first entry we'll call alpha, the second entry we'll call beta. And then applying t inverse will give us alpha times e to the 2x sine 3x plus beta e to the 2x cosine 3x. So something that looks like that. But now if we evaluate this at 0, which is our final goal, we have the 30/30th derivative evaluated at 0 is just equal to beta, and that's it. Because sine of 0 is 0, e to the 0 is 1, and cosine of 0 is also 1. So that means our value is minus I over 2, 2 plus 3i to the 30, and then plus I over 2, 2 minus 3i to the 3030. And that may seem like a crazy number, but I think that's probably the easiest way to write this number down. And that's a good place to stop.